So far, I mainly discussed the upper bound for the mixing time. So in the second lecture, I mentioned the theory of coupling to prove that Markov chain mixes fast. And last time I mentioned the spectral method. So using the eigenvalue information, how can we prove that Markov chain mixes fast? And today I'll give you some methods to prove the opposite direction. So how to show that Markov chain mixes slowly. Okay. So the last part is about the lower bound. Lower bound for the mixing time. Okay. We take a set. So we have a total set omega. Okay. And we take a subset S, right? So we have S and S complement. Okay. So I will measure some kind of shape of this set. So this is called bottleneck ratio of the set. Okay. So what does this mean? Bottleneck. Bottleneck is this, right? Like this. This shape, right? And this is called some kind of bottleneck, right? Okay. So bottleneck ratio of the set measures this portion of the set. So mathematically, this is defined as pi s is defined by, so we take a point in S and point in S complement. So we pick one point inside this set and outside this set, okay? And then measure the transition color, okay? So we have pi x p x y, and we take some normalization, okay? And as before, pi is invariant measure, okay? So pi is invariant distribution. Okay. Yeah, so this is called the bottleneck ratio of the set, and this this measures this kind of shape. If we take the minimum of this value among all sets, then this is called, so we take the minimum of this value for all set, okay, whose mass is less than 1/2, then this is called isoperimetric constant. Okay. So this is exactly the, so I think you heard about this before in differential geometry class, right? So this isoperimetric constant is the Markov chain analog of isoperimetric constant in differential geometry. So they have very similar meaning, right? So this is exactly some kind of boundary of this set. So this is some kind of boundary of the set. Okay. So what does boundary of the set mean? Boundary means that boundary of the set describes this kind of blue edges. Okay. Therefore, the conclusion is that isoperimetric constant of the set equals boundary divided by volume of the set. Okay. So this is the reason why this constant is same as the isoperimetric constant in differential geometry, right? So in differential geometry, we learned that isoperimetric constant is the length of so the volume of boundary divided by volume of the whole set, right? So this is exactly same as that, right? Boundary divided by volume. Okay. So this is the reason and motivation why we call this constant by isoperimetric constant theorem. Mixing time. is always greater than 1 over 4 times isoperimetric constant. Yeah. It gives the lower bound. So what does this mean? If isoperimetric constant is very, very small, okay, so if pi star is close to 0, then this right-hand side is a large number. Therefore, mixing time is very large. Mixing time being large means that Markov chain mixes slowly. So if we think about the simple random walk on the graph whose isoperimetric constant is very, very small, then you will get a large mixing time. Okay, so this is a relation between isoperimetric constant and second theorem. Okay. So if we additionally assume that pi is reversible, okay, then there is an interesting relation between spectral gap and isoperimetric constant. So this is a relation between them without referring to mixing time. So what is a spectral gap? Recall the spectral gap is difference between the trio eigenvalue and second. So now I'll mention the last theorem, which gives another lower bound for the mixing time. So this is the last theorem. Maybe this is fact, not theorem. So this is called distinguishing statistics method. Okay. So suppose that, so let's define the expectation of some function under the probability measure mu. So this is very obvious, right? Okay. So what is the expected value of some observable or some statistics under the measure? It is just linear sum, linear combination, right? This is definition of expectation of the function. And it is suppose that we have, so we are given two measures, but assume that difference of a particular function f under these two measures are quite large. So this is large. Okay. Okay. So here sigma is the variance. So sigma is variance. Sigma square is the average of variance. Okay. Okay. So this means that there is a certain function f for which difference of expectation under two distribution is very large. Okay. If you can find a certain function f, if you can find this function f, then one can deduce that mu and nu are quite far away. Yeah. So this is quite useful. This is quite useful to prove the lower bound, because if you set nu to be stationary measure, so this is stationary, okay? And if mu is the distribution of time t Markov chain, so you are comparing the distance between time t Markov chain and stationary distribution. So I want to claim that stationary one and time t Markov chain one, they are not closed. They are not closed. I want to claim that. Then what should we do? Another way to prove this is that if you can find a certain function, some artificial function, such that expectation is very different, then you can automatically claim that total variation distance is already large. Okay? So this is the method of distinguishing statistics. So here the crucial business is that you need to find this kind of nice particular function, which gives you a very different expectation. Okay. So what does this mean? Cutoff means that this total variation distance, so this is a time, and this is this is d. Okay. So recall that dt measures the distance between time t Markov chain and stationary one. Okay. So so we learned that in maybe second lecture, we learned that if we fix a state space and if we fix a Markov chain, then as t goes to infinity, this function decays exponentially fast. Okay, but there is for certain Markov chains, there is a cutoff phenomenon which says that the total variation distance drops immediately. So it decreases, right? Because we learned this, right? So mu p minus up decreases, right? So it always decreases. So it decreases, but at some time it decreases so fast, and then it decays like this. Okay. So there is an abrupt decrease in the total variation distance, and this phenomenon is called cutoff phenomenon, and this is verified for a certain class of Markov chains. Question is about it is not about the mixing time, but instead it is about the heating time. And cover time. So what is this? Okay, so what is this? So there's terminologies, heating, right? So heating time is just the first time that Markov chain hits a set, right? So there is a set, this is a total set, and let's choose a subset A, okay? And Markov chain starts from some point, okay? And if it moves like this, right? Okay. And one can consider the first time that Markov chain hits the set, right? So this first time is defined by the heating time, okay? So this is the heating time. And it is very important problem to find this heating time, right? Because if you remember the problem set 1, okay, so we defined the notion of harmonic function, and the last problem number 6 in the problem set 1. So there is a nice relation between the harmonic function and the heating time, right? So there are so many. So heating time is very related to the harmonic function, and so many concepts in the analysis. So it is very important to find and compute the heating time for broad classes of Markov chains. And what is the cover time? Cover time is the first time that Markov chain covers everything. Okay? So what does this mean? So cover time means that suppose that we have 6 many states, okay, and there's a Markov chain, okay, jumps to here, jumps to here, jumps to here, but it can go to the first time, right? This is possible, and go here, here. We want that this arrives the last point, but it may go back to here, okay, and go to here, but at some time it covers the last point, right? So cover time is the first time that Markov chain covers all points. Okay? So cover time is the first time that Markov chain visits all points, all states. Okay. Yeah. So why is this important? So why do you study this? So this seems a bit artificial. So why is this important notion? So the reason is that there is a very nice relation between cover time and heating time and mixing time. All of them are related. So one can bound a mixing time in terms of cover time. One can bound a mixing time in terms of heating time. So all of these concepts are very related. So it is also very important to find the cover time. And the last thing is, so far I discussed only this discrete case, right? So discrete time, discrete space, only finitely many state space, right? So everything is discrete, right? But one can extend to this continuous version. So there is a continuous version. Okay. So what is the continuous version of simple random walk? It is, maybe some of you know, maybe it is called Brownian motion. Okay. So Brownian motion is a continuous version of simple random walk. So yeah, and so yeah, what is this? So instead of lattice, we have a full Euclidean space. Okay, so for example, let's think about R2. Okay. So starting from origin, it behaves like this. Yeah. Okay. This is a continuous process, and the important property of the Markov, important property of Brownian motion is that each time distribution is Gaussian. So at each time t, the behavior of the Brownian motion is always Gaussian. So that's one important thing, and it satisfies the Markov property. Yeah. So behavior of Brownian motion is similar to behavior of simple random. They are similar. And there's also generalization of this. So in this case, this is continuous path, right? So there is no jump. It is continuous. And the discontinuous version is called the Levy process. So this means that process is no longer continuous. There is a jump. So this corresponds to the Laplacian. And this corresponds to non-local operator, because there's a jump, like fractional Laplacian. Okay. This is Laplacian. So yeah, so we know that the discrete version of Brownian motion is simple random walk. But what is the discrete version of Levy process? So what's the discrete version? It is not simple random walk, but okay. So in the case of simple random walk, we jumped only to the adjacent points, right? So for example, if we are at this location, there are 4 many candidates, right? Here, 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 right? So this is the underlying reason why Brownian motion is continuous, because it only goes to the nearby points. But in the case of Levy process, it can jump to everywhere. Here, here, here. So all jumps are allowed. So if you take the continuum limit of this, then you will get a Levy process. So yeah, and yes, yeah, these two are very active topics now. So what's the property of Brownian motion, Levy process, and connection to the partial differential equation? What's the regularity of the solution, and so on. So there are so many questions related to this.